Welcome back to AP Chemistry. In this video, we're going to be starting a topic which involves the rate of chemical reaction, something that we call kinetics. Now, when we say kinetics, or the rate of reaction, some students get a little bit confused as to what we're talking about. For example, you might recall that in an earlier part of AP Chemistry, we learned about thermodynamics. And this part of chemistry is trying to answer the question, will the reaction go? Is it actually going to take place? Is it going to be thermodynamically favored or not? Then we learned about a topic called equilibrium. And this involves how far will the reaction go? Is it going to go to completion, or is it going to go halfway, or more than halfway, or less? Well, that's what equilibrium is all about. In this lesson, we're starting to discuss kinetics, which is how fast will the reaction go. And so when we say kinetics, we're talking about the study of rates of chemical reactions and the factors that affect those rates of reaction. So just because a reaction has a large equilibrium constant and goes 100% to completion does not necessarily mean that that's a fast reaction. Now, we can take a look at the rates of some reactions. I think intuitively we know that some reactions are just faster than others. For example, if we see this reaction right here, looks like something is on fire. Well, that seems to be a pretty fast reaction. When you see flames and smoke and things like that, that's a good sign that it's a very fast reaction. Well, if we take a look at this reaction here, this seems to be a car that's rusting. And that's a reaction that is eventually going to go to completion, so it would have a very high equilibrium constant, but it's also very slow. And so this particular reaction, if we're talking about a car that's rusting, that may take 10, 20, 30, 50, 100 years for this reaction to reach completion, but it is a very slow reaction. So this is what we're talking about when we mention the kinetics of a chemical reaction. So let's take a look at a sample reaction. So here we're going to take 2 molecules of dinitrogen dioxide, and it's going to decompose into 2 molecules of dinitrogen monoxide and an oxygen molecule. So for right now, we're going to focus on the reactant, the N2O2, and one of the products, N2O. We're not going to worry about the oxygen right now. We'll talk about that a little bit later. But let's take a look at a graph of the concentration of those 2 substances over time. So as you take a look at this, what do you notice about the rates of both of these substances? Well, it's interesting that the dinitrogen monoxide, the N2O, is a product, so it starts at a very low, 0 concentration, and then it goes up. And we look at the curve there, and we see that it has a certain curvature to it. And then we look at the N2O2, which is the reactant. It starts at a fairly high concentration, about 1.700 molar here, and then it falls. And notice that its curvature is basically the same as it was for the N2O. These 2 substances have the same curvature, as we would say, the same rate. And so the rates of both of those substances are equal, although they're going opposite in direction. And so let's talk about why that's the case. What do you notice about the coefficients of both of those substances? Well, here's N2O2. It's got a coefficient of 2 out in front of it. And then N2O also has a 2 in front of it. So it seems like both of those coefficients are actually equal, as we can see. And so that evidently has something to do with this. When the coefficients of the molecules are equal, well, then that means that the rates are going to be equal as well. So let's take this a step further here, and let's imagine this same reaction, but this time we're actually going to put a number on this. Let's determine the rate of change of N2O in the time interval from 0 to 50 seconds. And so that would be N2O, that's this curve right here, and we're going to start at 0 to 50 seconds. So that's about right here. And so whenever we calculate the rate of reaction, that's done by taking the change in the concentration of whatever that is, N2O in this case, and dividing it by the change in time. And so that means that we started, or we actually ended up at 0.5 moles per liter, as we can see right here on the graph. And it started at 0. So that's why we subtract that. 0.5 molar minus 0 molar divided by the change in time. Well, it's 50 seconds. It's a 50-second interval from 0 to 50 here on the graph. So that's why we subtract that. It's 0.5 minus 0 divided by 50 seconds. When we do the arithmetic there, 0.5 molar divided by 50 seconds is 1.00 times 10 to the negative second molarity per seconds. So those are the units that we're normally going to use for rate, molarity per some time unit, usually seconds, although if the reaction is slower, it could be per minute, per day, or per year if we had a very slow reaction. So when we take a look at this, we can see that the rate seems to be slowing down as we move throughout the reaction. So the reaction starts kind of fast, and then it slows down and it gets to a point where it tapers off down here toward the end, or possibly the close to the end of that reaction. So when we calculate the rate for these intervals, that's really not the best way to do it because there's some error involved there. The rate is always changing. If you really want to get a very precise way to find the rate at a certain point, at a very specific moment, well, you want to find what's called the instantaneous rate. And that's found by taking the slope of a line tangent to the curve. So if we're interested in finding the rate of this reaction, or the rate of N2O, at exactly, let's say, 100 seconds at that particular moment in time, well, we would draw a tangent line right here to that graph. So it's a little hard to do because it's hard to draw a straight line on this, but that is about the best I can do there. That's the tangent line to that graph at 100 seconds. And so if you find the slope of that line, that's the instantaneous rate. That's the rate at exactly that moment. That's kind of analogous to saying if you're driving in a car and you look at the speedometer and it says you're driving 70 miles per hour. Well, that's the exact speed at which you're driving at that moment. That's like the instantaneous rate. Well, if you are driving from where you are right now to some other place, maybe to the mall or somewhere like that, perhaps your average rate would be 50 miles per hour over that entire trip. That doesn't mean that you're driving 50 miles per hour the entire time. As you peel into the parking lot of the mall, you're probably not driving 50 miles an hour. If there's a red light before the mall, you're hopefully not going through that at 50 miles an hour. That's an average. Whereas the instantaneous rate, that's like what you see on your speedometer at any specific moment. So here's a question. How does the rate of this reaction change as time progresses? Well, hopefully you can look at this and see that the rate starts out at a high level. The slope is pretty high, either positive or negative in this case, but then it tapers off and it gets slower as the reaction progresses. Now, let's try this example here. If the rate of change of N2O in the time interval from 0 to 50 seconds is 1 times 10 to the negative second molarity per seconds, estimate the rate of change of oxygen, O2, over that same time interval. Well, what we want to do is focus on the coefficients. So you may notice that the coefficient of N2O is 2, and for oxygen it's understood to be 1. So that means it's a 2-to-1 ratio. the rate of N2O is twice whatever the rate of O2 is. And so if N2O is 1 times 10 to the negative second, we have to find basically half of that. And so when you divide that out or multiply by 1/2, you get this number right here. So it's 5 times 10 to the negative third molarity per seconds. Now, we could do the same thing and estimate the rate of change for N2O2 over that same 50-second time interval. So we have this same, there's our 2 right there. And so we see that the mole ratio is 2 to 2. So that means that the rate of change of N2O should be the same as the rate of change of N2O2. So if N2O was 1 times 10 to the minus second, then the N2O2 should be equal to that. So that's why it's also going to be 1 times 10 to the negative second molarity per seconds. Now, notice that no matter whether we're talking about a reactant or product, by convention, and this is just the way we do it, all rates are given as positive values. That's just how we do this. It's analogous to if you're driving in your car and you're driving north, your speedometer says 70 miles per hour. If you're driving south, the opposite direction, the speedometer still says 70 miles per hour. It doesn't somehow magically say negative 70 miles per hour, because that wouldn't make any sense. Rates are always given as positive values. Well, let's take a look at another concept, the idea of writing a rate law. And so in order to write a rate law, we have to have some experimental data here. We can't just have a balanced equation. So let's imagine that we have this equation right here, and we're given some data. And here we have 3 experiments. And for each one, we're given the initial concentration of both reactants, ClO2 and hydroxide, and we're also given the initial rate of reaction. And we're being asked to find the rate law. Well, the first thing we have to do is let's find the order, what's called the order of the reaction with respect to the first reactants. Let's do ClO2. So in order to do that, we have to find 2 experiments where ClO2 would be the only reactant that's changing. And I notice that experiments 1 to 2 seem to have that, because hydroxide from experiment 1 to 2 is constant. It's not changing. It's 0.03 in both of those. But ClO2 here is changing. It's tripling. It's going from 0.02 to 0.06. So that is a tripling of its concentration. Now, what happens to the initial rate? Well, it goes from 0.0276, or 0.00276 rather, to 0.0248. Now, if I divide that out on my calculator, it looks like it is going up by a factor of just about 9. So if the concentration goes up by a factor of 3 and the rate goes up by a factor of 9, then what is the power that goes here? 3 to what power is 9? Well, we'd say 2. And so that means that ClO2 is second order. Okay, that is second order. And so we would say second order for that one. Now let's do the same thing for hydroxide. Let's find the order of the reaction with respect to hydroxide. We have to do the same thing. We have to find 2 reactions where hydroxide is the only reactant that's changing in concentration. And I'd say experiments 1 and 3 would be good here, because from experiment 1 to experiment 3, ClO2 is not changing. So that means we can use hydroxide here. So from experiment 1 to experiment 3, do you see that the concentration of hydroxide is tripling? And what happens to the rate from experiment 1 to experiment 3? Well, if you key this into your calculator, it looks like it is also tripling. So 3 and then 3, what power is that? 3 to what power is equal to 3? Well, it's a 1. So we'd say that the order with respect to hydroxide is first order. All right, so now that we have the orders determined, so we have second order for ClO2 and first order for OH negative for the hydroxide, now we're going to move on and actually write the rate law for this reaction. Now the rate law for pretty much every reaction has the same format. It's always going to be written as rate, you always write the word rate, equals K, which is something we call the rate constant, times the concentration of the first reactant, I'll just call it A, raised to a power, the order, which what we can call maybe Y. And we do that for all of the other reactants as well. If there's a reactant B, reactant C, we raise those. So it's the same idea here. The rate law is just going to be rate equals K times ClO2 to the second power times the hydroxide concentration to the first power. Hopefully, you can see that those powers correspond to the orders that we calculated on the last slide. So 2 is the second order, 1 is the first order for hydroxide. Well, now once we have the rate law for the reaction, sometimes we might ask, what is the overall order? Well, the overall order of the reaction is just the sum of the two individual orders. So we have 2 here plus 1, so the overall order is third, overall third order reaction. Now, sometimes, in fact very often, we're asked to calculate the value of this value right here, the K, which is the rate constant, with correct units. They always want the correct units for these. Now notice this is a lowercase k. It's a rate constant. It's not a capital K. It's not an equilibrium constant like we have been studying in the past. Now, calculating the rate constant is basically just taking any one of these three experiment values here, these data sets for any one of those experiments you choose, and plugging it into the rate law right here. So we're going to use that rate law once again, and we're going to plug in numbers from any one of those three experiments. I'm going to choose the first experiment, and so when I plug those numbers in from the first experiment, we get this. And so the rate, as you can see, was just 0.00276 molarity per second. That goes in for rate, equals K, which is what we're solving for, times the concentration of ClO2, which is 0.02 molar, right from the data there, squared. And then the molarity of hydroxide was 0.03 molar, so that's right out of the data set here. So now we just solve, and when we do that, we get 230, and the units are 1 over molarity squared second. Now, the numbers should be pretty easy to get. If you don't see where we get the units, the easiest way to do that is realize that molarity squared times molarity over here is molarity cubed. So to get rid of that, we have to multiply this side times 1 over molarity cubed. And if we do something to one side of the equation, we have to do it to the other side as well. So 1 over molarity cubed over here, and this molarity cancels with one of those three, leaving us with 2. So that's how we get 1 over molarity squared times seconds as our unit for the rate constant. Let's try one more example with this here. Let's take the rate law for this reaction using this data. Now the first thing we have to do is find the individual orders. And so we'll start with NO, and we need to find two experiments where NO would be the only reactant that's changing. And it looks like experiments 1 and 2 would qualify because bromine is constant from 1 to 2, but NO seems to be doubling, 0.02 to 0.04, so it's doubling. Now, what's happening to the rate from experiment 1 to experiment 2? If you plug this into your calculator, you'll see that in experiment 2, it's 4 times what it is in experiment 1. 5.6 divided by 1.4 would be 4, so it's quadrupling. And so do we see a power that would work here? 2 to what power is 4? Well, it's 2. So that means that the reaction is second order with respect to NO. Now, how about bromine? We do the same thing. We find 2 experiments where bromine would be the only reactant that's changing. And it seems like 1 and 3 would qualify, because from 1 to 3, the NO is not changing. But from experiment 1 to 3, it looks like bromine is doubling, 0.03 to 0.06. So if it doubles, what happens to the rate from 1 to 3? Well, 1.4 to 2.8, it looks like it's doubling as well. So 2 to what power equals 2? Well, that's a 1. So we can see that it's first order with respect to bromine. And so if that's the case, we can write the rate law just like this. We have our second order there for NO and the first order for bromine. Now, what is the overall order of the reaction? Well, just add the individual orders. 2 plus 1 would be third order. How about if we calculate the rate constant of the reaction with appropriate units? Once again, we're going to plug into that equation, to that rate law, using any one of these experimental value sets. You can use any one you want to. I'm going to use experiment 1 just because it's the first one there. So plug it in. And when I do that, I'm going to multiply these here. So 0.02 squared times 0.03 would be 1.2 times 10 to the negative 5th molarity cubed. And I want to multiply both sides by 1 over molarity cubed. And of course divide both sides by the 1.2 times 10 to the negative 5th. And for our units, you can see the units will be 1 over molarity squared seconds. And the number is about 120. And so this is a little introduction to kinetics, and this also shows how to write rate laws, how to deal with the graphical nature of this. And so I hope you learned a little bit of chemistry. Hope you learned a little bit about kinetics and rates of reaction. If you did, then please give me a thumbs up, and I hope to see you in the future on this YouTube channel where we can learn some more chemistry together.